Good morning, good afternoon, good evening, mammals. This is the last video that I'm going to be posting before spring break, where I talk about periodic trends, and we're going to use the effective nuclear charge as our justification for all of these different properties and how they change on the periodic table. These are the properties that you need to be able to talk about and use effective nuclear charge and Coulomb's law to justify their relative values, either looking horizontally or vertically as they change on the periodic table. Coulomb's law, if you don't remember, I believe it's on your formula sheet, but formula sheets don't really matter because you're taking it at home, is this. And it's going to be the handy thing, even though you're not going to have any numbers to plug into it, this will show to the grader that you understand that the forces behind all of these properties are attractive and repulsive forces between a positive nucleus and the negative electrons. So Coulomb's law says the force is proportional to some constant times the charges divided by the square of the distance between them. Things that make them further apart are going to increase the denominator, which is going to weaken the force. Things that make the charges higher, this is where the effective nuclear charge comes in because it's like our net force. It kind of combines both of these into one number because it takes into account the attraction for the positive protons, subtracting out any electron-electron repulsion. An increasing effective nuclear charge will increase your numerator, which will increase your force. That's where effective nuclear charge is going to come in. So I'm going to go through each of these individually and give you kind of the AP safe words way to talk about it. I also posted a link to an article that I really like. It's called The Do's and Don'ts of Periodic Trends. You should definitely print that or have that handy on test day as supplemental material to help you guide you writing your FRQs should you have to talk about a trend in a property. Starting off, I'm going to use atomic radius. I've got a periodic table here with the atomic radii, and you can pretty quickly see that in this corner we have the largest radius, and in this corner we have the smallest radius. It's technically measured by finding half the distance between two nuclei of identical atoms, because the electron cloud is sort of like our atmosphere. You go up from the Earth and it gets thinner and thinner and thinner and thinner until at some point you're in outer space, but there's no leaving town sign there. So chemists just take two nuclei, which are very small and easy to measure exactly where they are, and cut the distance in half. And it's generally the opposite of effective nuclear charge. In our previous video, we said that helium has the highest effective nuclear charge, and this lower left corner, they left francium's row off here, has the lowest effective nuclear charge. So your safe words for talking about this, if you're going to make a horizontal comparison, the question asks you why a pair of elements in a horizontal period on the periodic table have the relative sizes that they do. You're going to say elements further to the right have higher effective nuclear charge, which contracts the electron cloud into a smaller space, and you're going to drop Coulomb's law, put your formula in there, say that the effective nuclear charge is increasing the numerator, and which increases your force, drawing them into a smaller radius. If you have to make a vertical comparison, this is where effective nuclear charge kind of has the confounding factors, where as we go down the periodic table, you increase the number of protons, which increases your attraction, but you're also increasing the number of inner shells, which increases your repulsion. So you're not really going to get into that. You're just going to say that elements further down the periodic table are placing electrons in higher, more distant energy levels, and leave it at that. Next up, ionic radius. This chart can be a little bit difficult to read, so let me clarify it for you. The blue circle that you see here on the metal side, that is the size of the neutral atom. The darker gray circle that you see in the middle of it is the size of the cation, because ionic radius is measuring the size of the most common ion. And for metals, your most common ion is going to be a cation. On the nonmetal side, the kind of beigeish circle, sorry Greg, on the inside is the size of the neutral atom, and the outer dark gray circle is the size of the anion. Again, because the most common ion that you're going to have for nonmetals is going to be an anion. And this size is going to be related to whether we've formed a cation, or that should say anion. If you're forming a cation, you have a metal, cations are always going to be smaller than their neutral atomic radius. This is because they've lost electrons, but if you leave it there, just saying that they lost electrons, they get smaller, you're not going to get any points. You need to say when they lose electrons, the amount of electron-electron repulsion decreases. This has the effect of increasing the effective nuclear charge. With the more effective nuclear charge, this is going to contract the electron cloud more. Drop in Coulomb's law into your discussion and refer to it. You're going to see this on everything. If you have a periodic trend question, you need to sort of name drop Coulomb's law formula to show that you get that it's this attraction repulsion thing going on. Additionally, if you're dealing with an alkali metal, an alkali earth metal, or aluminum, some of these guys over here, you may also be forming a cation that results in the complete loss of their valence shell. So if I were to draw sodium has 11 protons, most common nucleus. Isotope has 12 neutrons, and it's 1s2, 2s2, 2p6, 3s1. The most common form of sodium is sodium plus. And it forms that by losing that 11th electron, which completely gets rid of its former valence shell. So now it's smaller for that reason too. Not only have we decreased the electron-electron repulsion, we've also gotten rid of an energy level, leaving just two closer into the nucleus levels behind. Anions are generally going to be, not generally, always going to be larger than their neutral atomic radii. And this is because exactly the opposite reason. Since they've gained electrons, the amount of electron-electron repulsion has increased, and that decreases their effective nuclear charge. This expands the electron cloud. This is how you're going to talk about it if you have to talk about a neutral atom compared with its either cationic or anionic radius. You might also be asked to compare two different cations or anions to each other. For this comparison, I'm going to use the third period because it's a complete period of 8 elements without any D block. That can cause some exceptions. So, sodium, magnesium, aluminum. I'm going to leave out silicon for this example because it just would kind of mess things up. Phosphorus, sulfur, chlorine. What you can see is a general trend of decreasing ionic radii as you go across, but you've got this break when you switch from the cations getting smaller, jump in size, to the anions, which are now larger than their neutral atoms, and they get smaller again. The way to talk about this is within the cations, the greater the number of electrons that you've lost, the more electron-electron repulsion has been lost, which is in effect creating more effective nuclear charge, drawing the ion's electric cloud in closer. When we compare these three, aluminum has lost 3 electrons, and so it's lost the most repulsion. The effective nuclear charge has come up. All of them are isoelectric with neon. So they've reached an electron configuration of 1s2, 2s2, 2p6. So their electron repulsion is comparable because they have the same electron configuration. However, sodium has 11 protons, whereas aluminum has 13 protons. So roughly the same electron repulsion, but aluminum has the most protons, creating the most effective nuclear charge and drawing its electron cloud in the closest. We can flip the script for our anions getting smaller. Phosphorus has gained the most electron repulsion because it has gained 3 electrons, whereas chlorine has gained only 1, because we're not making even comparisons here, apples to apples. We're just comparing the most common ion, which for phosphorus is gaining 3 electrons. Similarly, we can think about what they're isoelectric with. They're isoelectric with argon, but phosphorus has 15 protons. I like writing protons in blue. Phosphorus has 15 protons, chlorine has 17 protons. So we're comparing things with the same 18 electrons, same electron configuration, so we're going to have comparable electron-electron repulsion, but a smaller attractive force, smaller effective nuclear charge for phosphorus. Continuing on with the theme of ions is a property known as ionization energy. It is the energy to remove an electron. It is always endothermic. If it wasn't endothermic, that element wouldn't have that electron to begin with. These energy values that you see listed here are the energy that you have to give to remove the first electron from an atom. Your safe way to describe this is if you're comparing things horizontally, elements further to the right have a higher effective nuclear charge, which increases the amount of energy needed to remove an electron. Drop in Coulomb's law that your numerator is going to be greater because of the higher effective nuclear charge, greater attractive force, more energy required to remove it. Similarly to atomic radius, as you go down, you're not going to talk about kind of effective nuclear charge here. You're going to leave it as just more distant energy levels. And this reduces the attraction because you're increasing the denominator in Coulomb's law. So they're easier to remove. With ionization energy, we can also measure multiple ionization energies, and these are the energies to remove additional electrons. What you can see in every case is that each electron, here's removing the first, here's removing the second, third, the fourth, the fifth, removing each additional electron always requires more energy than the previous electron to remove. This is because as we're removing them, kind of like what we talked about with the cations, you're decreasing the amount of electron-electron repulsion. This increases your effective nuclear charge, requiring more energy to remove the subsequent electron. So this is going to be your answer if you have to talk about why the second ionization energy is higher than the first for any element. Another trend that we can see within this, at least when we consider the things that tend to become cations. So I'm going to highlight the things that tend to become cations. I'm going to leave out this stuff here on kind of the right edge of the periodic table that would rather gain electrons, and this trend is about losing electrons. Whoopsie. Highlighter. So if I focus on these, we can see kind of a pattern where there's the largest increase in energy. Lithium has the biggest increase in ionization energies between the first and the second. Beryllium has the highest increase between the second and the third. Boron between the third and the fourth, and carbon between the fourth and the fifth. Same pattern repeats itself in the next period. And this is related to how many valence electrons that they have. 1, 2, 3, 4. 1, 2, 3, 4. The large increase in energy happens once you've run out of valence electrons. Now, weaker AP kids will say, oh, they've reached their noble gas state, and the noble gas state is stable. You're not going to do that because you're not going to get any points for that. That's like Gen Chem level of explanation for what the atoms, quote, want, and that noble gases are, quote, stable. We're going to do better than that because you're going to say that the large increase occurs because you are now switching from removing valence electrons to inner shell electrons that are at a smaller distance from the nucleus. So if we compare magnesium and sodium, one S2, 2S2, 2P6, 3S1, 1S2, 2S2, 2P6, 3S2. Sodium, this first electron is removed relatively easily. The second electron is now an inner shell electron, which experiences less electron-electron repulsion, therefore much harder to remove. For magnesium, you've got to remove 2. Now this second one is still higher than the first one, because going back to the effective nuclear charge video, I said it's kind of a falsehood to say that electrons don't repel each other. They do. We've still decreased our repulsion a bit, but we decrease our repulsion a lot when you go and try and remove this third one, because now it's an inner shell. So if you're asked to compare the ionization energies where you have this large jump, you're going to answer that the increase occurs once you're starting to remove inner electrons, which are closer to the nucleus, therefore they have a higher effective nuclear charge, drop in Coulomb's law. Okay. The last two trends are very, very similar with each other. So I'm going to define the trends for you, and then we'll look about the kind of AP safe language here in a second. Electronegativity is the ability for an atom to attract pairs of electrons that are currently in other bonds. So if I draw a simple structure here, and I have a water molecule, which is a very polar molecule, this oxygen has a large ability to attract electrons in this bond. That's what we're talking about with electronegativity. Its ability to attract bonded electrons from some other atoms. A closely related trend, before I go on, let me point out to you, no values for most of your noble gases. A closely related trend is electron affinity. This is the energy released when a neutral atom gains an electron. It is generally, though not always, exothermic. I don't like the sign conventions on this, and I've seen both sign conventions used on the AP exam. When I think exothermic, I think negative because it gives me energy. This chart is listed, and since it's the energy released, whatever, be careful with the signs on this. This chart, imagine all of these signs flipped, but it's the best chart that I could find. Let's think about the ones that won't be exothermic, the ones that are endothermic. Those are going to be the things that don't really have much attraction for an electron, like your noble gases over here. So these are the guys that are going to be your endothermics. And we'll come back to that in a second. Both of these trends roughly follow effective nuclear charge, excepting for the noble gases, which we will come back to in a bit. And you're going to explain it the same way that you've explained everything else. Elements further to the right have a higher effective nuclear charge, which increases their attractive force, so they have a greater ability to attract electrons to themselves. In the case of electronegativity, their greater effective nuclear charge means that they give off more energy when they attract an electron, when they gain an electron. Vertical comparison, repeating a theme here, that the electrons are going to be further out from the nucleus, reducing the attractive force, so they have lower abilities to attract electrons to themselves. Something I want to point out with this before we go on to the noble gases and why they're kind of an exception to this. You notice that fluorine is the most electronegative element, but does not have the highest electron affinity. This is related to why hydrogen fluoride is a weak acid. Hydrofluoric acid is a weak acid, and the rest of them are strong. Even though it has the greatest electronegativity, since it is so small, it has an unusually high amount of electron-electron repulsion if it were to gain an electron, and that actually decreases its electron affinity and decreases its ability to act as an acid, because if it dissociated as an acid, those are some really sloppy dots. I'm going to do better than that. It's putting 10 electrons into a very, very small space, and that creates so much electron-electron repulsion that it is actually not as favorable as it is with chlorine. Now we'll move on and talk about why the noble gases are kind of exceptions to both of these. The noble gases, the additional electron, either giving it to it or attracting it from a bond, would now have to go into a new, higher, more distant shell, reducing the attractive force. Kind of like with the ionization energy trend, you're not going to say that they're noble gases and they're stable and they're happy, you won't get any points. You need to say here that since their current valence shell is full, so if I look at neon, 1s2, 2s2, 2p6, if it were to attract an electron or be given an electron, that electron would have to go into the next highest shell where it has a much lower effective nuclear charge. It makes it difficult for us to measure electronegativities for these noble gases, and in the case of electron affinities, it makes it to where they are endothermic because there's so little attraction there. There's so little attraction there that it has to be forced to take on this extra electron. So this would have, whatever sign conventions that they're using, this would have the opposite sign for the other electron affinities. One thing, and this goes to some of the other exceptions to it that you might notice, there are some other elements that have endothermic electron affinity, and you might be kind of confused and like, wait, nitrogen wants electrons. It wants actually 3 electrons. Why is it endothermic? And that's because this is the electron affinity to give it 1. And I'm going to tie into that electron orbital notation that we talked about earlier. Nitrogen, 1s2, 2s2, 2p3. In orbital notation, it looks like this: 1s, 2s, 2p. It has all unpaired electrons in the p. So if you're talking about giving it just 1, it's going to have to go into a shell that already has 1 there, and here we get repulsion. And so the N-1 ion is not stable, and that's reflected in its endothermic electron affinity. So if you happen to be asked about one of these that aren't noble gases, that would be it. I highly, highly doubt that you would have to do that. What I would anticipate is that you would have to talk about a noble gases electron affinity or a noble gases electronegativity, and you're going to answer that by saying that the added electron would be going into a newer, higher shell. So, I hope this gives you some background into it. Like I said, I find that linked do and do not thing to be super, super helpful. I would definitely have that printed off and at the ready for the AP exam. This is my last post before spring break, so enjoy. I hope you have a relaxing spring break. And as always, take care of yourself and others, practice good hygiene, and I'll see you on the flip side.